think we should get started. Hello, everyone. Welcome to this conference. So this is a conference about quantum computing and quantum dynamics. We will have 4 sessions. I'm the chair of the first session, Jianzi Zhou. So in each session, we'll have 2 talks, 45 minutes, and 30 minutes is for the presentation, 15 minutes is for the discussion. I think without further ado, we can start the first talk. Our first speaker will be Matthew Fisher. So he's a local participant, and he will talk about entanglement dynamics in hybrid quantum circuits. So Matthew, please go ahead.
Okay, can you see me and hear me?
Yes, I can see you and I can hear you.
Okay. All right, well, thank you so much, Jianzi, and also thanks to the other organizers, Tom, Vedeka, and Sagar. It's a pleasure to tell you a little bit about some things that have been going on over the last couple of years on entanglement dynamics in hybrid quantum circuits. And my apologies to any of you who might have heard some version of this talk before. Hopefully there'll be a few new things in here. But what I'm interested in are open, non-equilibrium, dynamical quantum phases and phase transitions. And this work has predominantly been done with Yaodong Li, who's a graduate student here at UCSB, and Xiao Chen, who is a former KITP postdoc, who's now at Boston College. And so in particular, what I want to tell you a little bit about is a measurement-driven entanglement transition and a dynamically generated quantum error correcting code which follows thereafter. So in looking at, okay, here, let me see if I can, there we go, change that. So in looking at non-equilibrium dynamical systems, it's often useful to look at entanglement entropy, which is what we will be doing here. And just to remind you, thermal entropy basically counts the number of states, and at finite temperature for an equilibrium system is extensive. The entanglement entropy, which is what we're going to be focusing on, is a property of a pure state psi that lives in some big region. It could be an eigenstate of a Hamiltonian. And then one looks at the reduced density matrix by integrating out the regions of the system outside of some subsystem A, and defines an entanglement entropy, which measures basically the entanglement between the quantum degrees of freedom in A with those quantum degrees of freedom outside of A in region B. And for equilibrium thermodynamic systems, there's something called the eigenstate thermalization hypothesis, which says that the thermal and entanglement entropies are essentially equivalent, at least in the thermodynamic limit. Okay, but I'm not going to be talking about equilibrium systems. I'm going to be talking about out of equilibrium systems, and we'll be focusing on entanglement dynamics. And initially, I want to mention closed systems. And for a closed quantum system out of equilibrium, there are 2 ways one can look at that. One is with a quantum quench. So if one takes some non-integrable one-dimensional Hamiltonian, for example, and evolves an unentangled initial state with the Hamiltonian dynamics, one can look at the entanglement, which starts unentangled, and what one finds, as in this paper by Kim and Hughes, is that the entanglement spreads ballistically, even though the energy diffuses. So entanglement tends to grow very rapidly and sort of reaches its maximum possible value consistent with energy conservation. One can get rid of energy conservation entirely if one looks at dynamical circuits which evolve with unitary dynamics, as shown schematically here, a figure taken from a paper by Nahum, Ruam, Vijay, and Ha. And so what they did and considered is evolving a quantum circuit with qubits in one dimension, qubits coupled together with 2 qubit random unitary gates, starting with an initial unentangled product state. And they find, just as in the Hamiltonian dynamics, that the entanglement spreads ballistically into a maximal entropy state in this case, since there's no energy conservation. So generally, entanglement dynamics in out of equilibrium closed systems, the entanglement just grows ballistically, and at long times in the steady state, the system is entangled as possible. Okay, I'm in trouble advancing my, there we go, oops. Okay, so entanglement grows. Now, what I want to do is consider controlling the entanglement growth via measurements. So just to illustrate this, imagine that Alice and Bob share a singlet state, each with a spin 1/2. They then have an entanglement entropy of log 2 between one another. But if Alice, for example, measures her spin, after measuring her spin, Alice and Bob's spins goes into a direct product state. It becomes unentangled, and their entanglement entropy after the measurement is actually equal to 0. So what one sees is that a local measurement induces disentanglement, and that's going to play a role throughout the talk. Now, with measurements, which is what we want to consider, we necessarily have an open system. So this is what maybe the most important slide in the talk, trying to distinguish between two different types of open quantum systems. The first class here in the left column is perhaps more familiar. Let's say one has a system of quantum spins which are coupled to a bath or an environment. And let's say we start with an initial pure density matrix. Well, under the dynamics, through coupling to the environment, that density matrix rapidly becomes mixed. Essentially, the environment measures the system, but the results are lost. No one's keeping track of those results of those measurements. And this leads to decoherence. And for a Markovian bath, at least, the dynamics of the density matrix, the mixed state density matrix, evolves with the Lindblad equation. Okay, what I want to be focusing on is a second class of open quantum systems, which one might call monitored systems, which are indeed monitored by a, quote, observer. So here one again starts in, let's say, an initial pure state, and that state evolves unitarily and then is measured and stays as a pure state. And the observer who makes those measurements keeps track of those measurements. And so the wave function evolves as a pure state. And the dynamics then can be described not by Lindbladian equation for the mixed state density matrix, but can be described in terms of the quantum trajectories of pure state wave functions. And it's in this second type of open system that I want to focus on in the rest of the talk, where one will see there's a measurement-driven entanglement transition. Okay, so in particular, what I want to focus on are spatially extended systems, and specifically a one-dimensional circuit of quantum qubits with measurements, so an extended monitored system. And here what serves this purpose well are what are called hybrid quantum circuits, which involve both unitary evolution and measurement gates. So the canonical model that is studied often in this context are qubits which are evolving with 2-qubit unitary evolution. And that unitary evolution, as I mentioned earlier, induces very rapid entanglement growth. But that is then interspersed with single qubit measurements which induce disentanglement. And so there's a competition between the entangling growth due to the unitaries and the disentanglement due to the measurements. And what we've been interested in is exploring the competition between the unitary evolution and the measurements as we vary the amount of measurements one is making. This parameter P is basically measurement frequency, the frequency that we choose to make the measurements in this random circuit. And then we follow the wave function quantum trajectories. And there are a number of references and some of the early papers I've just mentioned here. So what is the phase diagram for this hybrid circuit? Well, we can almost guess what it might be. The initial state, which we're going to start with, is unentangled. And we're going to imagine running the circuit dynamics to long times. And at long times, we have a pure state density matrix. And then compute a bipartite entanglement entropy, dividing the qubits into a region A and a region complementary to that, let's say a region B. So what is the phase diagram? Well, for P equals 0, where no measurements are made, one has basically a random unitary circuit, and it rapidly evolves into a maximally entangled state. So that has volume law entanglement. What about in the other limit, where P equals 1, where we are measuring every qubit at every available time in the circuit? That rapidly disentangles the qubits from one another and drives one into an area law state. So one can ask, is there a transition at some finite value of PC? In particular, we're asking about the phase diagram where this measurement frequency runs from 0 to 1, and we're anticipating a PC which separates a volume law phase at low measurement frequency from an area law phase at high measurement frequency. And it's this entanglement transition that I want to focus on now. In order to do that, it's very convenient to use a particular special type of circuit called a Clifford circuit, because due to the Gottesman-Canil theorem, Clifford circuits can be efficiently simulated on a classical computer accessing over 500 qubits. And so, in brief, a Clifford circuit can be described in terms of Pauli string operators, shown schematically here, labeled G. And one defines the state psi as a code word state if it's stabilized by L-independent commuting Pauli string operators, which are unit eigenvalue eigenvectors of the Pauli strings, of the stabilizers. And so the Clifford unitaries, what's special about them is that they map a single Pauli string into another single Pauli string. A general unitary would map a Pauli string into a linear combination of many other Pauli strings. So the advantage of following the Clifford unitary circuit is that one can follow the stabilizers without following the wave function itself. And that's much, much easier since there's only L such stabilizers. One can also make Pauli measurements within these Clifford type circuits. So for example, if we measure the Z component of, I guess, the jth spin, if Zj, the Pauli operator, anti-commutes with, let's say, with one of the stabilizers, G1, and commutes with the others, the stabilizers are modified appropriately under the measurement, with G1, replaced by plus or minus Zj, where the measurement outcome is the plus or minus 1. Okay, so now what I want to describe and tell you about are some numerics for a hybrid Clifford circuit where the unitary is taken from the random 2-qubit Clifford group and the measurements of the Z component of spin scattered in with probability measurement frequency P. And in the long time steady state, what's shown here is the entanglement entropy A, S sub A, as a function of the subsystem size L sub A. And what one finds is a phase transition. At low measurement frequencies up here, one has volume law entanglement. The system gets very entangled. But as one increases the measurement rate, one transitions into a region or phase where one has area law entanglement. So one thereby establishes through these hybrid Clifford circuits that the general phase diagram does indeed look like what I described earlier, that there's a volume law phase when one makes infrequent measurements and the system becomes very entangled, which is separated from an area law phase when one monitoring the system so frequently that one's pulling out all of the entanglement and one goes into this unentangled phase. Now, what's particularly of interest is this phase transition separating the volume law phase from the area law phase. And one can locate the transition by looking at a different quantity, which is related to the entanglement entry, which is the mutual information. So if one considers a system with periodic boundary conditions on a ring, schematically illustrated here, and considers two subsystems A and B, here taken each to be 1/8 of the system length, L. And one then computes the mutual information, which is given by SA plus SB minus SA union B, and basically gives one the amount of information that's shared between these two subsystems. And we can argue that in the thermodynamic limit, the mutual information is 0, either in the volume law entangled phase or in the area law entangled phase, where there isn't much mutual information shared at all. And right at the transition, we anticipate that the mutual information should go to a constant. And indeed, that's what one finds. Here, there's a nice peak, which we can use to look at the transition. These different curves are at different system sizes. One can do a data collapse to see if one gets a nice critical phenomena here. And here we've shown that data collapse and one can pull out a critical exponent which describes how a correlation length diverges, and it diverges with an exponent nu, which is around 1.4. One can also look at scaling collapse of the entanglement entropy itself. What's plotted here is the entanglement entropy at different system sizes and measurement frequencies, subtracting off the value at the critical point, plotted versus LA divided by psi, where psi is assumed to diverge with an exponent nu. With that same exponent nu of 1.4, one finds a nice data collapse. So one seems to have a really nice phase transition with scaling. One could do better. One can focus in on the critical point, on the entanglement phase transition right between the area law and the volume law phases, that is at P equals PC. And what one finds is that the entanglement entropy varies logarithmically with the subsystem size. And that's shown here on a semi-log plot. And this logarithmic growth of the entanglement, logarithmic dependence of the entanglement with system size resembles the ground state of a 1+1 dimensional conformal field theory. And so one can ask about, is there conformal symmetry at this critical point? And if there is, we anticipate that the mutual information, which I was looking at before, should depend only on the cross ratio, eta, defined here in terms of the endpoints x1, x2, x3, x4 of the two subregions A and B. And so here's some data taken by my graduate student Yaodong Li for different subsystem sizes, different locations of these regions A and B, and replotting all of that data versus this cross ratio, and one finds that data nicely collapses. And this is consistent then with conformal symmetry at criticality. In addition to the mutual information, one can look at correlation functions, which are upper bounded by the mutual information. So in particular, we can define in these regions A and B the total Z component of spin and look at an average squared correlation function. And I should emphasize this average squared correlation function cannot be written as a trace of any trace rho times any operator. And what one finds here is, as with mutual information, there's a peak at the transition. This peak gets smaller as the system gets bigger, and this is consistent, we believe, with a power law decay at criticality, which is not too surprising if one has a phase transition like this. So one of the confusing things about this entanglement transition is that there are three types of disorder present. So in the circuit that I've been describing, the three types of disorder are, firstly, there's a randomness in the unitaries that are selected to make up the circuit. The second type of randomness is the locations of the measurements, these open dots. And the third type of randomness is intrinsic to quantum mechanics and is the randomness in the measurement outcome. Well, we can consider trying to get rid of some of those random components by looking at circuits with translational symmetry. And so I have three different circuits shown here and three different scaling collapses for the entanglement entropy measured in those three circuits. The first is a Floquet-Clifford circuit where the unitaries are periodic, but the measurement locations are still random. We can, on the second circuit, make the measurement locations periodic and keep the unitaries random. And finally, on the bottom here, one can get rid of all the randomness, taking Floquet unitaries and periodic measurement locations, with the only remaining randomness being the measurement outcomes. And in all three of these cases, one gets a nice phase transition with the exponents the same. So somehow randomness, while convenient to look at numerically and also to look at analytically, is not essential, it doesn't seem to be, to the transition. One can go beyond the Clifford circuit by looking at much smaller system sizes and where one can still make progress on the computer. And here's some data shown for the mutual information at different Renyi indexes n in a circuit in which one has Floquet unitaries, which are of sort of an Ising form. and with generalized measurements, not projective measurements as I've been describing before. And here there's a parameter lambda, which measures basically the strength of those measurements. And when lambda is 0, no measurement is made. And when lambda is 1, it's a projective measurement. So what's plotted here then is the mutual information as a function of this measurement strength lambda. And one finds a nice peak at a phase transition, the measurement-induced entanglement phase transition. And in this circuit with Floquet unitaries and generalized measurements, the only randomness again that's present is in the measurement outcomes themselves. Okay, in the remaining time, what I want to do is focus on the volume law phase. It turns out the volume law phase is pretty interesting and not really that well understood. One feature that we find numerically from these Clifford circuits is that in addition to the volume law entanglement entropy, which grows with the length of the subsystem L sub A, there's a background in the volume law phase which varies subdominantly with an exponent which is around 0.38 in the Clifford numerics. And we can understand this at least qualitatively via mapping to a stat-mech model, which I'll describe briefly now. And then I'll turn to a dynamically generated quantum error correcting code at the end. So the mapping to the stat-mech model is really quite beautiful, and there's a number of authors that have been looking at this, both in unitary circuits and with unitary circuits with measurements. So in particular, what we're interested in here, and where these mappings to the stat-mech spin model work the best, is where the unitaries are taken from the random Haar measure. That's 2 qubit unitaries over the U4 group. And the measurements with measurements, and these are mapped to sort of 2-dimensional effective spin models or generalized Potts models in the space-time circuit. And what's interesting here is that even though one is doing real-time dynamics, non-equilibrium real-time dynamics punctured with measurements, in this statistical mechanics model, one has an effective theory which looks like, in which space and time look the same, and it looks basically Euclidean, space and Euclidean time. Well, what are the phases in the stat-mech model? Well, the volume law phase, as we'll see, corresponds to the ordered phase of the stat-mech model. You can, think about the stat-mech model as being, for example, an Ising model, which has a ferromagnetically ordered phase. The area law phase corresponds to the disordered or paramagnetic phase of the stat-mech spin model. From these stat-mech models, one can deduce how to extract the entanglement entropy, which is the main thing we've been looking at. And the entanglement entropy, it turns out, is equal to the free energy cost for changing the boundary condition in region A. So here is the space-time region of the circuit, and here's the final time slice. And there's a sub-region A in which the boundary conditions on the effective stat-mech spin model are different, let's say spin down, than they are outside of that region A, where they're spin up. And so in the volume law ordered phase, which is the ferromagnetically ordered phase of the spin model, one expects an entanglement domain wall. And the entanglement domain wall has an energy per unit length, and that gives one a free energy, which is proportional to the surface tension times the length of the entanglement domain wall, and accounts for the volume law phase in this volume law phase of the Clifford circuit, or of the circuit. The area law phase, on the other hand, corresponds to the paramagnetic phase, where the entanglement entropy and the free energy is of order 1, and that's because basically the spins in this effective spin model have completely disordered and the domain walls have proliferated. One can also look at the fluctuations of the entanglement domain wall, and this is really where one can understand the background to the volume law entanglement entropy. So we describe that basically using the simplest mean field type description, which we call capillary wave theory, where here y of x parameterizes the domain wall, and we integrate over all possible complexions of the domain wall, weighting the domain wall energy by the length of the domain wall. And one can push through this calculation, and what one finds is that in addition to the volume law term coming from the surface tension, there's a logarithmic subdominant piece coming from the transverse fluctuations of the entanglement domain wall. And this was found in a sort of lattice version of a similar model by Fan, Vijay, and Vishwanathan and Yu, where they found a universal coefficient of 3/2 within essentially a sort of capillary wave theory. But this actually differs from the Clifford numerics, which rather than a logarithm background gave a small power law of 0.38. So one sees that capillary wave theory, again, does not capture quantitatively the nature of the volume law phase. The entanglement domain walls are somehow more complicated. And it's possible that what's important in these spin models is taking the replica limit, and the domain walls in the replica limit are going to be more interesting and more complicated, but we don't really understand that fully at this stage. There's a completely different way to look at this entanglement transition as a purification transition, and this was in some beautiful work by Michael Gullins and David Hughes, where the only difference with this Clifford circuit that they ran from what we were describing already is they started with a maximally mixed state where the thermal entropy is very high. It's L log 2. They ran the Clifford circuit out to times of order L and then computed the thermal entropy. And what they found is that for low measurement frequencies, the density matrix stayed mixed. This they call the mixed phase. But if they made enough measurements, if the measurement frequencies were above the critical value, the measurements rapidly purified the system, and they went into a pure density matrix at long times. And so what they found is a transition from what they call the mixed phase to a pure phase, where in the mixed phase, the entropy was positive or non-zero, the entropy density, the entropy was 0 in the pure phase. And they argued that the purification transition is actually really the same as the entanglement transition. The difference is that with the entanglement transition, we were considering the initial density matrix was a pure state, and the purification transition, the initial density matrix was a maximally mixed state. Okay, in the last part of the talk, I want to describe how one can think about the mixed phase in terms of quantum error correction. And just to remind you of Shor's 9-qubit stabilizer quantum error correcting code, there are 3 integers which characterize quantum error correcting codes: L, K, and D, which take on values 9, 1, and 3 for the Shor code. Here, L is the number of physical qubits, 9 in Shor's 9-qubit code. K is the number of logical qubits, which one encodes, in this case, in terms of these 0 bars and 1 bars, which are the logical basis states. And D is the code distance, which I'll talk about in a moment. In addition to these, an important thing here I want to emphasize is that in any of these stabilizer codes, the number of stabilizers is less than the number of physical qubits. M is L minus K, so it's the difference between the number of physical qubits and the number of logical qubits. And here there's 1 logical qubits and 9 physical qubits, and so the number of stabilizers is 8. In addition to the 8 stabilizers, one can define what are called logical operators, Z bar and X bar, which act like Pauli operators on the encoded qubit, 0 bar and 1 bar. And finally, D, which is an important parameter here, is what's called the code distance. And it's basically what one might call the shortest logical operator, or the logical operator with the fewest number of qubits. And it turns out that a code, one of these stabilizer codes, can in principle correct any error acting on D minus 1/2 qubits. And so the Shor code can correct any single qubit error. So generally, these stabilizer quantum error correcting codes, as I say, have fewer stabilizers than qubits. So now let's come back to the Clifford circuits that we were looking at earlier, where we had and argue that we have a dynamically generated quantum error correcting code. In the maximally mixed initial state, in the steady state, one has fewer stabilizers than qubits. M is less than
Matthew,
L.
can you wrap up quickly? We're going to have question time.
Okay, yeah, I'll just do a few more slides. Yeah, I'll try to speed up there. Thanks. So here one dynamically generates a code LKD, where L is the number of physical qubits, K is the number of logical qubits, and one can talk about and ask about the code distance, which I won't really have time to talk about in any sort of detail here, but I'll just sketch what one finds. It turns out one can argue that the code distance can be extracted by looking at the purified initial state with a bunch of ancillas and looking at when the mutual information between some subregion A and the ancillas vanishes. And so here's the way that you can get the code distance for the Clifford circuit by computing the mutual information, and one finds a code distance which scales with L to this same power. We can also look at the code distance from the entanglement domain walls, and what one finds, again, is that in the capillary wave theory, in terms of the entanglement domain walls, that we get a logarithmic dependence, in this case of the code distance, rather than the power law dependence in the Clifford circuits. So again, simple capillary wave theory does not capture quantitatively the nature of the volume law phase. Okay, second to last slide here. Let me mention experimental access. What's challenging here is that one has to follow the quantum trajectories, first of all, but to extract the entanglement entropy or other physical observables requires multiple copies of the same wave function. And to reproduce the same wave function requires post-selection on all of the measurement outcomes. Basically, if one runs a circuit and finds some measurement outcomes, one ends up with a pure state. To end up with that same pure state on the next run through the circuit, one has to get the same measurement outcomes. And so this will involve enormous amount of post-selection on those measurement outcome results. There are proposals to overcome this challenge, and one in particular by Michael Gullins and David Hughes has some early experimental support on some beautiful ion trap experiments, ion trap quantum computer by Chris Monroe's group, and maybe Michael will talk about that a bit tomorrow, I'm not sure. One way one can overcome this challenge is to use Clifford circuits. And in Clifford circuits, the measurement outcomes can essentially be forced. One can use error correction to change a wrong measurement outcome. And of course, Clifford gates can be implemented on a quantum computer. So let me just wrap up the summary. So we've basically been considering non-equilibrium quantum dynamics in open quantum systems, which are monitored by an observer, in which measurements are made and notated. And we've seen that there's a quantum entanglement transition driven by the competition between the unitary induced entanglement and the measurement induced disentanglement. And that entanglement transition can also be viewed as a purification transition. There's an enormous number of open questions here, ranging from what's the universality class of the transition in one dimension or in higher dimensions. There's a lot of questions about the nature of the volume law phase, which I certainly feel I don't understand. The entanglement domain walls, which is a very nice simple picture, are not described by capillary wave theory. There's the role of the randomness. The randomness plays an important role in sort of analytic derivations of spin models, but doesn't seem to be important, at least in the Clifford circuit phase transitions. One can think about other dynamical phases or quantum error correcting codes in such monitored open systems. And most interesting of all is to try to see some of these things experimentally on, for example, ion trap quantum computers. Okay, so that's all I had to say, and thank you for your attention. I can take some questions.
Thank you. It's a comprehensive and nice talk. Now it's time for questions. So there are about 100 participants. So to avoid traffic jam, if you have a question, please raise your hand or type in the chat, and I can call the name. Please. Okay, I can ask a question. So Matthew, so you So you show the evidence of conformal invariance by showing that the mutual information is a function of the cross ratio. But that, I think that is a evidence for the conformal invariance on the boundary, but is there evidence for the space-time conformal invariance?
That's a really good question. I mean, one can certainly show that there are power law correlations inside the bulk of the circuit by bringing in ancillas, which one entangles with the circuit, let's say at two different points, and one looks at the mutual information between those. So, you know, I think most of the evidence comes from the boundary conformal field theory. But it's clear that the bulk of the circuit has, you know, is where the phase transition is taking place, and is conformally invariant.
Does that depend on the protocol you use? Because you list the 3 protocols with different types of randomness.
Well, we've only really checked for the conformal symmetry. Predominantly, we've checked for the conformal symmetry, in which all 3 types of randomness are present. So we don't have direct numerical evidence that the conformal symmetry is present when we eliminate the randomness in the bulk of the circuit, but I anticipate that it should be still, since we still have a phase transition and the critical exponents seem to be the same as with randomness present.
Okay, thank you. Other questions? So we encourage junior participants to ask a question. This is exactly the time. All right, so I can also ask a question about that domain wall interpretation with capillary wave theory. So in the purely unitary case, these domain walls are directed, meaning that they can only go, say, forward, and they cannot go backward.
Yeah.
But in the case with measurement, I think because the evolution is non-unitary, and so this domain wall can go backwards, so it's no longer directed. So why is it still a good choice to use capillary wave to describe it? Because I thought that could be a
yeah, so the measurement allows, I mean, yeah, so for a purely unitary circuit, the domain walls just run in the time direction and they cannot change direction. With measurements, the domain walls can turn and can go backwards. I mean, the reason why, you know, one would expect some sort of capillary wave theory would be valid is that the 2 phases in the spin model, which lives in the bulk of the circuit, have, you know, will have if those 2 phases are adjacent to one another, which they will have to be when one has a change of boundary conditions in this region A, then there will have to be some sort of domain wall that separates the 2 phases in this spin model. And a domain wall, you know, one of its most important features is that there's a surface tension, just as there is in a Potts model or an Ising model, you know, the domain wall between the up spins and the down spins. And so really the only difference here with the measurements is that the domain wall can run, you know, from one side, one point here on the final time slice to the other. And,
okay, sure. There are several questions in the chat. First one is Jerry. Why is mutual information between 2 regions expected to go to 0 in the entangled case?
Yeah, let me go back to that. Well, okay, the reason for that is that the regions A and B are smaller than the other regions. And so basically, there's so much entanglement between A and the rest of the system that there isn't that much entanglement between A and B. And in the thermodynamic limit, the entanglement between A and the rest of the system and between B and the rest of the system dominates and leaves, essentially vanishing mutual information between A and B. Yeah, that's a good question. Thanks.
Okay, question from Leo. What is the meaning of beta inverse temperature in the capillary theory?
Oh, what's the meaning of beta? Well, it's basically, what's important is the dimensionless surface tension. Did I have beta written in there? Maybe I didn't even, I probably did have it. I had it right there, and I dropped it there. Well, basically, so the effective temperature is determined in this StatMech model by the measurement probability P. And as P gets smaller, it's like going deeper into the ferromagnetically or magnetically ordered phase. And so it's like going to lower temperatures. So it's really a fake temperature. It's not really a temperature here. On the other hand, as the P goes to PC from below, as you approach the measurement transition from the volume law phase, the surface tension or the dimensionless surface tension beta sigma goes to 0.
The next question, Everett. So how does time distribution of the measurements affect the results? If the two measurements come in rapid succession and the system has little time to evolve, are they equivalent to one measurement?
Well, we're making measurements of the z component of spin. And so if you measure 1 qubit and you measure the z component of the spin and you find it up, and then you measure the z component of the spin immediately afterwards, you'll still find it up. So in that case, two measurements would be identical to one measurement. But what's important is that in this circuit, one has interleaving unitaries and measurements. And so it's important that between any two measurements, you have unitaries which can start entangling the results of the disentanglement that you get when you make the measurements.
Yeah. So measurements are displayed by the unitary. So constitutive measurements can be combined into one.
Sorry, yeah, I couldn't
Yeah, so I just said that the two measurements, so there's a unitary between the two measurements. And so if two measurements are consecutive, you can combine them. And so that's why it will not affect the results. Just to answer the question.
Yeah, okay.
All right. Question from Huan. I think this is the last question. Did you explore the phase diagram in the lambda p plane? Do you anticipate other phases or just two?
We anticipate only two phases. I think we might have looked in the lambda p plane, but I'm positive that there would just be two phases and there'd just be a phase boundary, separating them in the lambda p plane.
All right. Thank you. Thank you, Matthew. It was a nice talk.